Good afternoon and good morning, ladies and gentlemen. Welcome to Yokogawa's Analytical Web Seminar, an overview of analyzer system integration. We would like to thank you for taking the time to attend, and we hope you find this seminar helpful and informative. Before we begin, we would like to go over some housekeeping issues. The audio part of this seminar can be accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through your PC speakers. To hear the audio through your PC, select the Communicate tab and join the audio broadcast. This seminar will last approximately 1 hour. Towards the end of the presentation, where time permitting, we will have a question and answer section where a featured speaker will answer some of the questions received from the audience. If your question is not answered during the presentation, please be assured that we will answer them directly either via email or phone call. All questions should be submitted in either the question and answer window of the chat or the chat window located in the lower right-hand corner of your screen. Our featured speaker for today's event is Al Kanin. Al is a product marketing manager for Yokogawa's Advanced Analytical and System Integration. He has been involved with the sales and marketing of process analyzers, including GCs, for over 30 years. He has been with Yokogawa for almost over 2 years now. Prior to working for Yokogawa, he worked for CEMS Applied Automation, Rosemont Analytical, and Spectra Sensors. We would like to get the seminar started by handing it over to our featured speaker, Al.
Thank you, Sherilyn. Let's see here. There we go. Hey, a picture of me. As mentioned, I'll be talking about analyzer system integration. One of the things that you'll find out during this presentation is I hope to point out and demonstrate that there's a lot of important topics that are involved that need to be discussed and covered when dealing with analyzer system integration. And so to be able to cover at least briefly all of those different topics, we'll be moving fairly quickly. So if you find that there's something that you do have a question about, as she mentioned, either type it into the chat or the Q&A box, or if it's something that occurs to you after the fact, you'll see my telephone number and email at the bottom of this slide, and I'd be more than happy to address any questions that tend to pop up after the session is over with. The first thing I want to talk about, what is the role of the analyzer system integration? I mean, what is it trying to accomplish? Well, the first thing is since it deals with analyzer packaging, what you're trying to do is protect your investment that you've made in your process analyzers, whether they're gas chromatographs, oxygen analyzers, pH probes, or whatever type of device. Quite often, these analyzers are not always meant to be installed outside in the weather. And more importantly, they may not be designed to operate in hazardous or explosive environments typically found like in a refinery or chemical plant. Also, most analyzers can't directly sample the process sample itself without some type of conditioning, either to bring it into the right temperature or pressure range, perhaps do some filtering or flow adjustments. So often, extractive type analyzers, which would be installed in a shelter or box or cabinet, need some type of sample preparation or sample conditioning as part of the total package. The other aspect is, as I mentioned, is again, not all analyzers are necessarily designed to operate in a hazardous environment or a harsh environment. So the analyzers need to be packaged to provide a safe environment. Furthermore, maintenance technicians, when they go to operate and maintain these analyzers, may need to have some type of mechanism so that they can access their tools or laptop computers without violating safety codes. And then finally, in this day and age, analyzers generate a tremendous amount of data that's used for process control or environmental monitoring and such. And so part of a total package for analyzer system integration is to be able to collect all of this data, collate it, and then transmit it over standard techniques such as field bus, HART, Ethernet, or whatever the mechanism that's preferred for this particular application. On this slide, you can kind of see just a real quick schematic of these different elements. Of course, the first part is the analyzer itself, either mounted inside a walk-in shelter or perhaps it's a cabinet or a small box. But obviously, if it's an analyzer package, there's an analyzer somewhere. The next aspect is most analyzers that are involved in these types of projects are some type of extractive analyzers. In other words, we're taking the sample out of the process, cleaning it up, getting the right temperature and pressure, perhaps switching in a calibration gas or a zero and span gas to make it available to the analyzer when appropriate. Again, there might be some calibration gases involved. The unused portion of the sample would be returned back to the process. You can't just vent it into the air, not like the good old days where air pollution laws weren't quite so strict. There might be some effluent where there might be liquids or different gases that are left over from the slop during the measurement, and they also must be returned either to the process or a flare line or some type of recovery system. And finally, as I mentioned earlier, the data handling. It's no longer just simple 4 to 20s and contact closures, although that is still seen. Often they can get quite sophisticated with serial networks like Ethernet or HART or Fieldbus. And most importantly, all of this must be done while maintaining complete safety, both from hazardous area classification and toxic gases if they might be present. The first thing that you'll encounter when you deal with analyzer shelters or analyzer packages is there's quite a wide variety of packaging options available. The first is it might just be a simple panel where you take a piece of equipment such as a pH probe, mount it on a steel plate, bring all the tubing connections in and all the wiring connection in, and then you can just mount it out in the weather, maybe perhaps with a simple sun shield. Or if it's a small type of analyzer all by itself, let's say like a small oxygen analyzer, you might just put it in a small box or perhaps a freestanding cabinet for like a CEMS package. You know, this is perfect for small little small little applications. One other option is what I call the three-sided shelter, or kind of like looks almost like a bus stop, where you have 3 walls. And the analyzers and other types of electrical equipment are mounted inside there, and mainly you're providing some weather protection, but obviously you're not doing any temperature control because you're missing an entire wall. But one of the nice things is because it's an open ventilation system, you don't have to worry about the accumulation of explosive gases or hazardous gases, and so that can make meeting area classifications and hazardous area classifications a lot easier and cheaper. And then finally, there's the full-blown walk-in shelter, whether it's a steel building or something like that, where you walk in through a door, all the equipment's mounted in there, it's temperature controlled, often purged and ventilated, provides a great work environment for the analyzers and the technicians, but obviously it can be quite frequently the most expensive option. So when you look at your different options, you need to weigh the benefits versus the cost. And here's just a few pictures of some examples. For example, here's a gas density analyzer mounted on a plate that would then be mounted outdoors, or perhaps with just a simple sun shield over it. Here's a freestanding cabinet where I think it's a total sulfur analyzer in there, or perhaps a titrator. Yeah, it looks like a titrator, sorry. Where you can just open a door and everything's kind of packaged. It's nice and simple and cheap and small. You know, just perfect for when you just have a single analyzer to deal with. Here's a freestanding box with an oxygen analyzer in it and some sample preparation equipment mounted below it. There's a 3-sided shelter, or bus stop as I call it, where you can see a little small explosion-proof analyzer mounted in there. And again, it's just perfect when you're putting equipment in temperate climates like the Gulf Coast area. And then finally, of course, we have the classical full-blown walk-in shelter. You can see the door on the right-hand side there, and such as that. Other options include for the shelter is what the materials of construction. For example, here in the United States and many parts of the world, metal shelters or metal packaging is quite common, either steel, stainless steel, epoxy-coated, galvanized, depending on the requirements and the location of where it's going to be installed. Aluminum is often found for smaller packages where you don't have to worry about the weight so much. Fiberglass is becoming increasingly popular, mainly because it's very chemical resistant. A lot of the process environments can be quite harsh on steels and cause corrosion. And specifically, if you're going to be mounting on an offshore platform, like an oil rig or something like that, where you might have salt spray that can cause a lot of corrosion on steel and metal. So fiberglass is very popular for there. Over in Europe and other locations, one very common option is concrete shelters, where literally it's a big concrete building where everything's pre-mounted and such as that. A great, excellent thermal insulation, obviously very rugged, don't worry about corrosion, and such as that. And then within the shelter and on the outside, there's a technique called the unistrut infrastructure, where you actually have these long strips of metal where you hang the equipment and the tubing on it, and it allows for quite flexible hardware arrangements. And I'll show you here a picture of it in just a sec. Here we go, see some examples. In the upper left-hand corner, again, is your classical steel walk-in shelter with equipment mounted on the outside. The picture in the upper right, you can see some of the equipment that would be mounted inside, and it might be possible to see the little gray horizontal bars that are running across the width of that picture, and that's that unistrut I was talking about. And you can see it also a little bit on the bottom shelter running along the outside, and it gives you a lot of flexibility to mount and move equipment, pieces of equipment around for final installation. And that bottom picture is actually a photograph of one of the concrete buildings where it's exposed aggregate that would be going off to Europe. Some of the other shelter design issues, other than the material construction and the basic shape, would include topics like wiring and cable management. Here in the United States and Western Hemisphere, we take conduit for granted because it's very popular here. But if you go into other parts of the world, especially in Europe, they tend not to use conduit, but tend to use armored cable for hazardous protection for their wiring. Sample systems, again, to help get the sample in the right temperature, pressure, and flow. Those tend to be mounted on the exterior. You can kind of see that in the bottom picture there. Those big boxes are mounted along the outside. And this just makes it a lot easier to get access, and it also keeps the bulk of the sample on the outside in case of a leak. Now, obviously, in some climates, like Russia or Canada and such, you may still have to put the sample systems inside just due to the sheer cold during the winter. And what some customers will do is perhaps in those situations, they'll actually run a wall down the center of the inside of the shelter to split it so that one side would have the sample systems, again, to help segregate that in case of a leak, and the other side would be where the technician would be to normally work on the analyzers itself. In the upper and lower picture, you see the little rain shields that hang out along the outside. And again, this is just to help protect the technicians when they're working on the sample systems or perhaps the bottle racks and such as that, so that the hot weather or the rain doesn't go down the back of their neck. And you even see little lights along there so that during the night, because things always seem to happen during night, not during the convenient day, they can easily see what they're doing. You might need heated bottles for your zero and span calibration gases. Again, you might get condensation that occurs inside the bottle in cold climates. You see the doors on there, but for large doors, large shelters, safety codes often require a door at each end. That way, if there is an accident that occurs inside the shelter, they wouldn't find themselves blocked off from the only available door. And then finally, most shelters are designed to be dropped on a concrete pad. You can kind of see that on that upper picture. And this allows it to be much easier to install in place. But you do find steel plating. It's used for when you're mounting the shelter up high, up on rigging or up on an offshore platform. And even in extreme cold climates, a floor will be provided with insulation underneath to keep the cold from coming up from underneath there on the ground. One of the biggest topics that need to be discussed when working on an analyzer system integration project is the hazardous area classification. When you're installing this equipment in a refinery or chemical plant, you want to make sure that the equipment is safe and won't cause explosion or fire due to the electrical equipment. Most of the customers themselves, they define the actual hazardous area classification for the different areas inside their own plant. This is all part of their own internal safety codes and requirements. And so with that information, they could define to the manufacturer of the shelter what requirements are needed to be met. And depending on the location and where in the world, there's a number of different standards that are available. There, in the United States, there would be NFPA. Canada might use the Canadian Standards Authority, CSA, ATEX. which is common in Europe and other areas. And then finally, to help bring commonality to all the different standards, there's slowly but surely a growing global standard called IEC-EX. And depending on which code the customer defines that needs to be met, that would then dictate what has to be done to meet the safety requirements. If for some reason the safety requirements don't exist as far as being available for that piece of equipment, for example, Australia has a very specific code called the SAA, and not much equipment actually has that already pre-certified. But whatever the case may be, it's quite straightforward to bring in a local representative of that safety agency and have them do what they call a field or site inspection to make sure that for that installation it meets the requirements. So it'll be kind of like a one-off permission to be able to use the non-certified equipment for that application that would meet those codes. Just to kind of give you a quick overview of what's involved quite frequently when you start discussing hazardous area classifications, it helps to understand the different buzzwords and terminologies that are thrown around, just to kind of give you a little bit of a feel. For example, in the United States here, where we use the NFPA, which is similar to the CSA, the first thing you'll have defined is what they call the class. What type of component is it that might be present that could cause the explosion? For example, in the chemical industry refineries, it's typically some type of hydrocarbon gas or vapor. But I remember growing up as a kid in the Dakotas, we had wheat grain silos, and every now and then you'd hear about one of those exploding because you can get explosive flammable dust from coal bins or grain silos. So that would be called Class 2 type of a situation. And then finally, Class 3 would be like in the textile or carpet industry, where you'd have these very fine fibers from the textile mills causing potentially an explosive environment. So first thing to do is you define what class it is. For example, it might be Class 1 for a refinery. Oop, backwards, wrong way. Then the next thing is to define how likely is it for a hazardous situation to occur. The most common situation, hopefully, is what they call a general purpose environment. You know, that might be like in an office or something like that where there's very little or almost no possibility for a hazardous situation. You know, basically none of the hazardous gases actually enter into this area. The next is what they call Division 2, and what this means is normally there are no hazardous gases or dust or whatever present. But under plant upsets or unusual conditions, like maybe during a leak, then yes, something could occur. So it takes some type of failure or breakdown to cause a hazardous situation. Then finally, Division 1 means there's always the possibility. In other words, you're right in the plant itself, perhaps, where there's always the possibility that there's a hazardous gas present. And then finally, there's what they call the chemical group rating. It says, okay, now that I know that what the possibility is and what type it is, how easy is it for the ignition to occur? For example, groups C and D are your typical hydrocarbons, but things like hydrogen and acetylene are much easier to ignite, so they might be a group B or a group A, and so they would put a little bit more severe restrictions on the type of electrical equipment that can be used. So when it's all said and done, when you're defining the area classification, you would hear something like Class 1, Division 2, groups C and D. And that would then define what the area classification is for that area. So that says, okay, in that type of situation, according to code, I can use these pieces of equipment, but I cannot use those pieces of equipment. And so by knowing your area classification, it helps guide you on what will be used to have a safe environment. And there's a very similar structure for the other codes, such as ATEX, where they use what they call zones rather than divisions, but they got a Zone 2 rather than a Div 2, or a Zone 1 rather than a Div 1. And so you'll find a very similar, but not exactly identical nomenclature, but it's very similar. And then finally, you have what you call your T rating, and that deals with not so much an arc or a spark, but heat. You know, for example, let's say you had a heater or a motor that might get hot. You know, how hot can that temperature get before it would actually act as an ignition source? So you'll hear T ratings of like T1 through T6. And what that does is, again, depending on the types of chemicals that might be present, would restrict you on how hot the items can be. For example, if you had a very stringent T5 or T6, it's extremely difficult to find pumps and motors and air conditioner systems that meet those codes. So you want to make sure that you keep things safe without going crazy, or else you can get yourself boxed into a corner. Because when it's all said and done, it has a tremendous impact on the design and therefore the cost of the package. Obviously, it'll impact the electrical systems, whether it's explosion-proof boxes for your breakers, your light fixtures, they're behind explosive resistant designs and mechanical structures, your power receptacles. Air conditioning systems are heavily impacted. Closed-in shelters can get quite hot, so they frequently have an air conditioner. And to be quite honest, air conditioners are one of the biggest cost items to an entire package. You can easily spend $10,000, $20,000, $30,000 just on air conditioners because of their need to meet the hazardous area classifications. It's not where you just go down to your local Home Depot and buy something cheap. These are very specialized pieces of equipment designed for hazardous areas. And same with pumps and motors. If you get into an area where you have a lot of acetylene or hydrogen present, they're the group A and B, extremely expensive, where you just for the pumps and motors. So it has a huge impact on the cost. And it also has an impact on the analyzers. Not all analyzers are designed to be used in all different environments. So it starts impacting on what analyzers you can use to meet a solution for the customer. He says, I want to be able to measure oxygen or something like that, and perhaps you're having difficulty finding an oxygen analyzer that meets those requirements. So you have to do some special things to make that analyzer safe. One of the things you might do, for example, is what they call purging the entire shelter, where you actually bring in fresh, known safe air in large quantities and actually constantly flush out or sweep out the entire area inside that shelter. And basically what you're doing is you're preventing the accumulation of any hazardous gases. And this can be quite handy because what it does is it now reduces the requirements for your different pieces of electrical equipment, so they can be a lot cheaper. Obviously, it makes the analyzer maintenance a lot easier because your technicians can turn on their laptops and not have to worry about violating a safety code. But one thing to do keep in mind is if you do lose your purge system that purges that shelter, you might have to interlock and turn off all power to all analyzers and pieces of equipment mounted in there. And that may or may not be an option for, what they call mission-critical measurements, where you just can't afford to be turning something off because the air got lost. One thing that some customers will do is they'll say, well, not all of my areas of the plant have a high Division 2 or Division 1 requirement, so perhaps by moving it across the street or down a little bit further in the plant, I can reduce the severity of the hazardous area classification for that part of the plant. One of the tricks that we use, or not tricks, but one of the solutions we use for environment or for packages is if the analyzer doesn't meet the requirements for the area, you can purge the analyzer. For example, let's say I had an analyzer that doesn't meet Division 2 requirements or that Australian code I was talking about. You can actually mount the analyzer inside a box where, again, you bring in known safe air, maybe perhaps instrument air or plant nitrogen or something like that, and you actually keep a constant flow in there where there's no possibility for leaks or accumulation of a hazardous gas to accumulate there inside of it to cause a problem. You might have what they call X-purges, where I'm just trying to take a general purpose piece of equipment and move it in a Division 1 area, where if I have a loss of air because the air system got cut off by accident, I have to turn on alarm, and then I have to turn off the power to keep a safe environment because I don't want the analyzer operating now that I've lost my purge. But you also have some things like Y purge and Z purge, where I'm allowed to keep the power on because the analyzer itself perhaps is inherently safe. It's just not safe for particular situations. So depending on, again, on the safety codes defined by the end user or the area, you can use different types of purging systems with different interlocks. Most purging systems have some type of maintenance override system, so that way you can actually open the door to the box and not have the power cut off every time you're trying to do maintenance. And if for some reason purging is not an option, perhaps you're mounting the equipment where purging air is not available, they make explosion-proof boxes, big, thick aluminum enclosures where literally it assumes that if the analyzer does explode, it's all contained within that box. So these are certainly an option. They tend to be a little bit more expensive and obviously a lot more cumbersome to do maintenance, but they are an option. And one thing to keep in mind is that if you do have a fully enclosed shelter, typically most customers or most users say that if I'm a certain classification on the outside of the shelter, say Div 2 or Division 2, when I go inside, I typically knock it up one more level of severity, such as to Division 1. The idea is when I go into an enclosed area, I increase the possibility of accumulation of a gas or something like that. But again, that's all defined by the end user's own safety codes. Safety systems, in addition to explosive protection, can include things like safety monitors. Again, when you have an enclosed area such as a shelter, you want to make sure you don't have the accumulation of combustibles. So you might have combustible sensors mounted on the inside in case of a leak that's not picked up. If you're dealing with toxic gases such as cyanide, phosgene, H2S, it might be a very good idea to mount toxic sensors in there, again, to make sure that you're a safe environment for your workforce. And finally, you might need oxygen deficiency analyzers, especially if you're using plant nitrogen, because it's always possible that the plant nitrogen might leak and displace all of the breathable air inside there. So you want to make sure you have a safe environment for the technicians in there. You know, as always, it's important to monitor where you mount these different sensors at different heights and locations, so that you always make sure there's little pockets of pool of the gases that you pick it up. And in many situations, it's advisable to wire the alarm system such that if there is a unsafe condition, it'll actually trigger a warning light and a horn mounted above the entry door. That way, on the outside, that way the personnel know it's safe or not safe to go inside. And some even will even send a contact closure to their own plant safety systems with their distributed control system. Another big area of design inside the analyzer shelter, as I mentioned earlier, was the heating, ventilation, air conditioning system. And in this picture, you can kind of see that on the right-hand side, that big box there of that picture. Again, it typically can be one of the most expensive elements of the shelter design. So a lot of thought needs to be done in this so that you buy the right size without spending too much money. For example, one of the things you want to be very careful about is to size it properly. Some pieces of equipment, like say chromatographs, have a high amount of heat wattage needed during power up, but once it reaches its operating conditions, the amount of heat or wattage needed drops tremendously. For example, it might need 1,400 watts during power up, but only 400 watts during normal operation. Well, when you add up all the wattage inside that shelter, you want to use the 400, not the 1,400, because that's what would normally be seen by the air conditioner, and you would be able to save a lot of cost on the air conditioner by having it sized properly. And many analyzers, like gas chromatographs, make it easy to capture their excess air used in their oven that is very hot and vent it to the outside, so you're just not adding to the load of the air conditioner. And also, since the air conditioner has a blower system and such as that, if you're going to have one of those, it also then makes it not much more difficult and not much more expensive to add a full purging system and ventilation system to the entire shelter. For example, you can see that on the picture there where you see this big gray stack going out above the air conditioner, where it extends up, let's say 25 feet in the air, where it's known that you'll have safe air to bring in that then be brought in to keep the entire shelter purged and ventilated. Other aspects of the shelter include the shelter utilities such as power, depending on the power requirements, one-phase, three-phase, such as that, how much wattage. Breaker boxes need to be defined and located and sized. Do they want expansion capability, or do they want to buy just what's required now? Analog power conduit and signal wires you might put in separate conduit so you don't get any noise on the analog outputs. Some very critical analyzers might even have UPS systems hooked up so you never lose power on them. And then some customers prefer to have shut-off switches by each major device rather than having to shut off the entire shelter or to go all the way over to the breaker box and throw the breaker. So all this needs to be defined as part of the total package and total solution. Instrument air. A lot of the analyzers use plant instrument air or plant nitrogen for heating of their internal ovens or purging of them systems. So these requirements as far as the amount of volume, the amount of pressures required need to be defined and built into the design of the system. I talked about the plant nitrogen, but there might be steam, for example, if you have to heat the sample systems to keep the sample nice and hot so it doesn't condense. And then always the question of, if you're building a shelter to house 6 analyzers, but you know that you're going to add 2 more a year down the road, it might be advisable just to go ahead and put the space in for those 2 extra analyzers, because that way it'll save you having to buy a whole second shelter just for those 2 analyzers. So knowing that up front, that can be laid into the overall design of the shelter. As part of the design of the shelter, it's frequently a good idea to ask for what they call manifold and header systems, because a lot of the equipment uses common utilities like air and steam, and they have vent and waste gases that need to be collected. So being able to collect them all together in a tube that's common to them makes it a whole lot easier, because it really does simplify the plumbing throughout the entire shelter. And you can kind of see these on those pictures, those long tubes, especially on the upper one that run along the horizontal there, where I'm bringing in all the gases and the vent gases. And, they're used typically for shared utilities like air or steam or carrier gas for a chromatograph. It's also used for recovery systems, again, where you want to collect all the gases that are not being used anymore to send them over to a flare system or such as that. Or perhaps you have liquids, like from a liquid system where you need to collect it. But you can see that in the bottom picture. You see that little tiny tank where it'll collect the liquids, and it has a little float in there. So once it gets to a certain level, the pump will kick in and it'll pump it out to a collection system. And so you can have a total reclaiming of the liquids also. So all of this needs to be defined and provided as part of the overall complete solution. There's also just the mounting. It's not as easy as it thinks of the analyzers themselves. Some equipment's meant to be mounted against a wall, and that certainly does simplify it, but some analyzers require access on all sides, as you can see on that top picture. So in that case, it makes it a little bit trickier in how you mount the equipment, because now you have to provide access from all directions. And you need to at least make sure you allow enough room so that technicians get in between it and be able to get access to all the sides. And you also need to consider how you place it on the height impact, because if you put it too high or too low, you either need to get a step stool or get down on your hands and knees, as you can see in that bottom picture. Sure, it allows you to cram a lot of equipment in that same space to save some money, but it helps. Unfortunately, it reduces the maintainability of the equipment, which unfortunately means in the long run you may find your equipment going offline because it's just not getting the tender, loving care it needs. Analyzers themselves tend to have a lot of consumables. These can include things like carrier gas and calibration gas. So when you do your design and layout of the shelter or cabinets or racks, you need to allow room for this because they need to be mounted somewhere and then plumbed in and brought in. And these are particularly true of chromatographs or environmental monitor systems, because they tend to have zero and span gases and validation gases and blanket gases and purge gases and such as this. And you can have a tremendous amount of bottles, like you can see in that upper picture there, that can be needed. And so you can almost have an entire wall dedicated to nothing but cylinders. The other thing to keep in mind, again, is the data and signal wiring. Again, because of the explosive environment typically found in a lot of shelters, you often have to use either armored cable or conduit. So how you lay it all out and plumb it up can have a big impact, especially when you're having different junction boxes, like for the data signals, the power systems, the breakers, and such as this. And again, in this day and age, an important consideration is also Ethernet. A lot of pieces of equipment have Ethernet capability or some other field bus or HART protocol capability. So all of that needs to be considered on how that's wired in and brought to the outside so they can be then connected up to the final destination. One topic I want to spend just a couple seconds on here is the sample conditioning system. I kind of mentioned a little bit earlier that sample systems are a big part of analyzer system packages because what ends up happening, most analyzers that need packaging are extractive by nature. In other words, they take the sample out of the process to the analyzer where it needs to be temperature and pressure and flow and filtered so it's compatible to the analyzer and doesn't cause a lot of headaches. So all of that needs to be done as part of the design. And as I showed in earlier pictures, typically sample systems are mounted on panels or boxes on the outside of the shelter. And this, again, is to keep it so if there is a leak or such as that, it leaks on the outside of the shelter and not on the inside to keep it safe. Of course, if it's a cold climate, you might not have that option. But, you know, when the sample system is mounted on the outside, you need to make sure that you don't forget about, you know, heat tracing the tubing between the outside and the inside, and also to make accommodations for the wiring if you're trying to do the package yourself. Whoops. No. But it's critical that when you do the sample system that the design is done properly. You got to make sure that, again, as I mentioned, the temperatures and the pressures and the flows are all compatible with the analyzer so that it can operate properly. And most analyzers require some type of zero and span calibration or validation gases, and there needs to be some type of mechanism for switching all of this in so that once a day or once a week the equipment can be calibrated, and that all needs to be done in the sample system. But it all needs to be done properly because over these last 30 years when I've talked to customers and clients, I ask them, you know, what headaches do they have with their equipment, and it's almost never the analyzer itself. You know, 60 to 80% of their problems are with the sample system. Either their filters are not the right type or they're getting contamination between the different sample lines and it's causing strange readings. So it's critical that the sample systems are designed properly because it doesn't matter if you have the best analyzer in the world. If you've introduced a bad sample to it, you're going to get a bad answer. So most analyzer packages require at least some type of engineering review of the sample conditioning system design. Even if it's a standard application, you need to make sure that that application fits that standard design. So when you're dealing with a system integrator that does your shelters or your boxes, your cabinets, you know, one of the things you want to make sure you do is you chat with them of how much experience they have, not just with the shelter design aspects itself, but the sample conditioning aspects. Because again, I mean, the whole idea is you're trying to have analyzers to use. And so if you're not getting the right sample to the analyzers, you're going to have a lot of headaches. So one of the things I want to do is just talk a little bit about sample systems, you know, some of the things involved. Again, we want to make sure we take a sample out of the process. Usually it's a pipe or a conduit or a duct or something where I'm taking a sample out. I'm transporting it from the pipe to the shelter where the analyzer is installed. So I need to do that in a controlled manner. Again, I need to condition the sample, either temperature, pressure, flow, filtration, whatever's needed. I need to provide some type of switching so that I can switch between the stream and any calibration bottles that might be needed. I need to be able to return what's not used or what's the waste gases so that it can be captured and returned to flare system or vent systems. And most importantly, I need to do this and not drive the service technicians crazy. You know, if I missize the filters and they have to go out every couple of days to swap a filter element out, the analyzer is going to suffer tremendously for it. So here's like an example of an application where you can see the different sample system elements involved. In a refinery, I have what they call a cat cracker, and I have an analyzer here, and I want to take a sample of one of the streams. So I've got my sample takeoff of the gasoline line. I then got a primary sample system where I might do some pressure and temperature control and maybe a little bit of filtration very early. I then need to transport the sample, again, in a controlled manner so that it doesn't condense or whatever. I need to do the final cleaning, you know, the temperature and the pressure and the filtration. I need to return the sample. Again, I just can't dump it down the drain or dump it in the air, at least not this day and age, not like the old days. I need to have a mechanism to introduce calibration and validation gases. And then if the analyzers themselves have any vent gases or slop, that needs to be accommodated and captured and returned. So all of these elements need to be thought of and considered, including lag time. Again, the analyzer might be mounted 100 or 200 feet away from where the sample is taken because that was the closest place for the shelter. And I need to make sure I can transport that sample without a huge delay. And I won't go through all these different items here, but these are just a few of the key aspects of a sample system design. So again, when you talk with your system integrator putting a package together for you, these are a lot of the aspects that need to be in his mind and hopefully in his experience so that you get something that will perform adequately, meet all the design codes, and of course not have a high maintenance situation. So to do this, the first thing the system integrator is going to do is start asking you a lot of questions. So you need to prepare to answer things like, what is the total chemical composition of the stream? And not just during normal situations, but also during upsets. I had a situation occurred some years ago where we were monitoring building a sample system to monitor a stream in a refinery, and the customer forgot to tell us that during upset conditions, HF acid would be present in high concentrations. And unfortunately, the first time that happened, literally all the stainless steel within the sample system and analyzer dissolved. Not only was it a hazardous situation, but it unfortunately very costly because he had to buy all new equipment because he forgot to tell us that this is what occurs during an upset condition. I need to know the sample point temperature and pressure so I can make sure I extract the sample out in a proper manner. And I need to know what the return pressure and temperature is, where I'm going to bring the sample back to. I need to know information on any corrosives or particles, the distances between where the sample point is and where the shelter will be. Otherwise, I can't calculate accurately the lag time to make sure the flows are correct. Now, for some applications, they may be some off-the-shelf solutions, such as for CEMS monitors for stack gas analysis, or perhaps combustibles or air monitors where, I'm measuring air, where things can be a little bit more simpler and predictable. But when it's all said and done, most of them are custom engineered, and so it's key to have a partner that you work with system integration that has a lot of experience on how to do the sample system design. Otherwise, you're going to have a lot of headaches with your total solution. And here's just a few pictures of what sample systems look like. In the upper left is inside of a shelter where I have a emissions monitoring system, and in the bottom of that picture you can see the different sample system elements like the pumps and the filters and the liquid coolers. On the right-hand picture there is a picture of something that might go in a refinery where you see a lot of solenoids for stream switching, the heater at the bottom of the box there, pressure gauges, flow meters, shut-off switches, and such as that. And the lower left is a boiler feed water type sample system where you might have a pH and conductivity probes, perhaps a silica analyzer and such as that, all mounted on a big old panel so it can be dropped into place. One common package that's done with analyzer system integrators that I kind of mentioned is environmental monitors for CEMS systems. These are typically defined by either the state or federal governments by their environmental regulations to monitor NOx or SOx or CO, total hydrocarbons, HCl or such. And again, those are defined as well as what the ranges will need to be by the government and the mandated requirements. The sample system design, again, can be critical because they tend to be very hot samples, very wet samples, so you need to make sure that you don't get condensation occurring. But there's a lot of very well-defined solutions there, so it's usually not too bad. You just need to know what the conditions are so you can get the proper design. And also, most of them tend to be in a safe environment. By safe, I mean, non-combustible, like some of those Div 1, Div 2 situations. So it's a general purpose area, and so that's why, like, for example, in this picture here, you will see just a simple air conditioner used because I don't need to use one of those big expensive air conditioners. But what does become part of the package is most governments, either the state or local or federal or even international governments, have very strict requirements on what data is collected, how frequent, how it's stored, how it's reported, what happens when I get excursions, documenting when calibrations and maintenance are done. So the actual data collection and data acquisition can be as big of an element as any part of the entire package. And so when you talk to your system integrator for a solution, you may be able to find that he can make recommendations on what type of data acquisition system to provide that would meet the various codes and requirements for your city or state or government requirements. There's also typically involved what they call, as you install the equipment, relative accuracy tests or accuracy audits or cylinder gas audits, and these are all part of the commissioning and ongoing operation to prove the analyzer system itself actually works and it's actually accurate to a relative degree. And most system integrators, either directly or through partnerships through third parties, can assist you in making this all happen so that the equipment can be started up and certified, you know, if you don't have your own sources already from past experience. A couple of topics I want to go over now real quick is, you know, what happens if you're working on a project in some severe or extreme climates? For example, one of the things you heard me talk about was the air conditioner systems, and especially in areas like Saudi Arabia or other such areas where you can get into some very big requirements on the air conditioning systems. Matter of fact, Aramco, if you're familiar with them, typically require backup air conditioners. And if you want to avoid the cost of that, they say, well, then your equipment, everything installed inside of it needs to be suitable for use up to 65 degrees C. At the other extreme, you'll have the situation where in a very cold environment, such as Canada, Russia, Scandinavia, where you might have situations where you need to put insulation in the floor to keep the cold coming in through the floor. Your calibration gases need to be mounted in hot boxes so they don't get cold. And your sample systems may need to be mounted inside. And finally, things like offshore platforms. Frequently, if you put equipment on an offshore platform, you've got very small spaces, or they tend to be on scaffolding. So you need to be careful about that and how small or how large items are, and as well as corrosion resistance. A lot of salt spray will usually corrode most metals, so you tend to use fiberglass quite a bit. And I had one person ask if it was possible to get a copy of this presentation, and I think Sherilyn mentioned that this entire presentation is being recorded, and if you'd like, you can send me your email address, and if you caught the email address at the beginning there, and I'll be more than happy to forward a copy of the PowerPoint presentation to you. See here, the next topic is documentation. The whole wiring and plumbing and layout issues. That you make sure that if you have special requirements of either yourself or your final client and end user, that's all being met. Factory acceptance tests, since these are fairly complex packages, you want to make sure that everything's built the way you think it is and expect it to be. So factory acceptance tests are very common, where the customer or end user will come in and say, this is exactly what I want, and so forth and so on. And one of the things I always like to point out is a big area that people tend to forget, especially during the budgeting phase, is the shipping cost. As you can see in that bottom picture there, shelters can be quite big and cumbersome, and especially if you're going overseas, that entire shelter would be actually boxed up in the biggest of all crates that you can imagine. I remember a 12 by 30 foot long shelter boxed and crated and shipped overseas. And so the actual shipping and export and crating costs can be a huge element if not taken into consideration. So when you do have a project with a system integrator, what typically happens? Well, once you get to the, you define what you want, you issue the PO to the system integrator, the first thing he does is review your PO, we'll then look at does the PO match what was quoted, and are there any questions and, undefined areas. As you can imagine, as you've heard during this presentation, there's a lot of aspects that need to be defined or you can't go very far. So that's all worked through and worked with the client to make sure everything's done. And once everything's cleaned up and clarified, it then gets broke down to an operations and project manager to head up the entire project. Once everything's defined, then a kickoff meeting is typically held, usually to get all the different elements defined and the bill of materials set so that everything can be purchased, because some items can be quite large, long lead times, so you want to get that stuff ordered as soon as possible, but then again, not order the wrong thing, so you got to do it at the right time at the right place. And then once everything gets started, you get to the point now where you can start to submit drawings and bills of materials. And I did have a question that popped up asking about, does all of this apply to smaller packages like the pilot plants and such? Yes, it can. I've seen a lot of packages supplied to different pilot plants. Obviously, you wouldn't have huge shelters. You would have smaller boxes and cabinets and racks. But a lot of these different aspects do kick in, but also some interesting wrinkles. Like in a pilot plant, you may not have a lot of flow because the amount of sample you're actually making and creating is not very much. So sometimes how much sample and distances and how you capture the sample and return it is critical because you can't afford to waste anything. So yes, they can be appropriate for small applications and even pilot plants, but some other rules and rules of thumb do kick in just because things are a little bit different for that situation. And now that I've got basically everything defined and on order, you can start getting drawings sent to the end user so that he can confirm that everything's going to be laid out and defined quite properly. So you start seeing the approval drawings and everything starting to get built and the production is started and the test and QA gets involved to make sure everything's being built on time and on schedule. And then finally, when everything gets built as expected and as designed, the client has the opportunity to come in and do what I mentioned before was the factory acceptance test to say, is everything the way I expected it to be? And if not, we create what we call a punch list, which is kind of a to-do list of things to clean up. And so we'll clean up the punch list, get any drawings updated as necessary. And hopefully, but sometimes it does happen, but hopefully not, you may even have a second FAT, if you need to make large-scale changes. And then once you get everything defined and built and assembled and tested and approved, it's now time to package it and get it off to shipping and then ship it on out. And that's what's involved in the total overall project of a system. So to do all of this and to minimize delays and minimize confusion and minimize rework, as you can kind of tell by the past 45, 50 minutes of discussion, there's an awful lot of details that need to be defined. And if the customer and client doesn't define them, the system integrator either needs to guess, and of course Murphy's Law says we'll guess wrong, or we'll end up having to do a lot of costly rework and change orders. So to help, some of the things you need to keep in mind is, what type of shelter are you expecting? A full shelter, simple cabinet or box, or maybe a rack. Again, if you're like a pilot plant, you won't need a whole shelter. Materials of construction. What the types of analyzers are, or even if you don't know the analyzer type itself, maybe you don't buy that many analyzers. You just say, I need to measure oxygen. Most system integrators have a lot of experience, decades worth of buying and installing equipment, so they can make recommendations to you of the types of analyzers that might be best suited for your application. But if you do have a preferred supplier, obviously you need to let the system integrator know what that is. And again, this complete stream data that I talked about when I talked about sample systems, both normal and upset, and whether you want some expansion capability and such. So more questions are popping up. There we go. Yeah, okay, I think I'm under control. So, types of analyzers, and most importantly, if it's a hazardous area such as a refinery or chemical plant, what is your plant, what is your company, your client defining? Because they have to define it. The system integrator doesn't. He doesn't have that authority. As far as, is it Div 1, Div 2, Class 1, and such as that? And do they prefer a purged shelter or not? Does the customer have any safety requirements? Some customers have internal safety standards that say, in these situations, I need to monitor for hazardous poisonous gases or oxygen and such as that. So obviously that needs to be defined. Are there any electrical requirements or restrictions, you know, conduit versus armored cable, lighting requirements. Everything can be done. It's just a matter of money. Circuit breakers and such as that. Shelter options, you know, the air conditioners, headers, calibration systems, rain shields, even tagging. You know, do you want plastic tags or metal tags? It can all be done. It's just a matter of money. And, of course, other information that's good to have is, you know, what utilities are available. You know, do you have plant nitrogen and plant steam and plant instrument air? Are there any special documentation or testing requirements? Some customers do have special forms that need to be filled out, and it's good to know that up front so that that can be taken into consideration during the engineering and construction of the analyzer. And, of course, any special shipping or crating requirements. And so you have all of these different aspects that need to be defined. And what's important is when you start looking at system integrators, and sometimes when you say, well, why is one quote from one system integrator twice the price of another? Well, chances are something was not defined, and so one system integrator made one assumption, and another system integrator made another assumption. You know, maybe it was the air conditioner sizing or something like that. And so suddenly I've got a quote for $30,000 and a quote for $60,000, and you're saying, well, that guy's either crazy or something like that. And chances are it's just because there was data missing, and you're not comparing what we call apples to apples. So when it's all said and done, analyzer system integration, it's a lot more than it seems. And hopefully, you know, and I do apologize for moving so quickly through this presentation. It is a lot more than it may seem. It's just a lot more than purchasing a shelter. You need to have complete and accurate specifications. Otherwise, you'll get into those situations where I talked about where you're just going to get a lot of random quotes from system integrators, and chances are they'll all equal out to about the same price by the time the change orders are done because one guy didn't include half the stuff you deep down really wanted. So a big part of that also is just the experience of the system integrator, especially with the sample conditioning system design. Again, you could have the best analyzers in the world installed inside there, but if they're getting a bad sample, you're just going to spin your wheels. And so if you find yourself on a project and you just don't have a lot of experience with shelters, maybe it's something you don't get involved with a lot. Again, most analyzer system integrators have been doing this for many, many years. And so they can make recommendations on analyzers to meet certain measurements. They can help you with writing specifications and doing what they call front-end engineering and design, you know, feed studies. They can assist typically with spare parts, commissioning, training, and such as that. Again, it's just as much or as little of that help as you want to include in the project and such. So anyway, I do want to thank you for your attendance. Again, I want to apologize for the fast pace through this, but basically what I wanted to do was just to give you a feel that analyzer system integration is a very important element in overall analyzer installation and measurement. Unfortunately, it tends to be a lot more complicated than most people think and expect, and so it can create a lot of headaches if you don't go into those details. So with that in mind, here's some information about who to contact for any additional information, such as copies of the presentation and such. My name, again, is Al Kanya, but if for some reason you can't get a hold of me, we have two other people that get involved in this, and that's Dave McMillan and Ron Edelman. And so if you have any questions, I'll see if I can figure out how this Q&A thing works. And in the meantime, I want to thank you again for your participation.
Thank you, Al, for a wonderful presentation. Some of the questions that have been asked are from Yokogawa representatives that aren't familiar with analyzer system integration and our capabilities. So those questions we will have to answer directly one-on-one since these presentations are meant for end customers and not to throw our capabilities in people's faces. They're more meant for what is this kind of thing.
Yeah, and so if you do have those types of questions, again, feel free to drop me an email, and what I can do is send you a copy of the presentation and some summary material that'll just give you a little bit more of a feedback and background on this, for sure.
So if no one else has any other questions, the emails there are provided. You have Al, you have Dave, and you have Ron. Al is the product manager once again. Dave and Ron are our outside Yokogawa sales managers that deal with system integration and all of the advanced analytical products. But we would like to thank you for coming to the seminar today with us, and I'd like to mention that it is actually recorded and will be available for replaying within 24 to 48 hours on our website, and we hope to see you online in some future seminars. Thanks, and have a great day, everybody.
Thank you.